Let's look at one more. We previously showed that it's possible to derive incompressible Navier-Stokes equations from the nonlinear Boltzmann equation. We don't particularly know here about deriving a Boltzmann equation from the particle systems easily, but it can be done. Both arguments together should provide a complete derivation of incompressible Navier-Stokes equations from systems of particles. Still, the approach remains mostly unsolved even today, which is amazing because of the importance of the equations. We look to a recent strategy in history from Lanford, and it's the only one known to this day. Let's look at it. It consists in studying the asymptotics of the first distribution, Fn1, of the distribution function f, given by the following equation in equation 202. F1 at time t and z will be defined as the integral of Fn tz of all integrations of the distribution. We can define the marginal or order of S in the set 1n by 203. Will correspond to the probability of S particular particles. For example, in the case of functions that are tensors, we can write 204. It's the product of F, with F as a probability, and it'll hold as 205, given S. Lansford theorem is stated this way, without proof, which can be found online. Consider n hard spheres of diameter epsilon, which is very small, on a multidimensional periodic box, TD, in time from 0 to 1 in d dimensions, with d greater than 2, so greater than 2 dimensions. We can write 206 that Fn0 of Zn is basically the average of the products, and F is a continuous density, such that the norm of F e to the mu plus beta over 2 v squared is less than or equal to 1 in all time and space, for some value of beta greater than 0, and mu is some real value. The limit from the mesoscopic to the macroscopic descriptions of fluid dynamics will correspond by taking some parameter alpha and letting it go to infinity in the Boltzmann equation and rescaling it in time. The particular limit of the macroscopic to mesoscopic description will correspond to taking n is to infinity, and it's known for small times or only for the order of alpha to -1. This unfortunately prevents it from combining both limits to go from particles to fluids. There's some particular cases which are linear where progress has been made on Hilbert's problem. It's been proved already that the distribution satisfies a heat type equation in the limit for n going to infinity using linear Boltzmann equations as an intermediate step, and the parameter alpha goes slowly to infinity with n. Consider this theorem of an initial distribution in 229. Here, z, or math script z, is normalizing constant.